Morning.
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 How are y'all?
Doing good.
Ugh. Right.
바꿔놔.
How are y'all doing? Good. Good. We are on. It's Wednesday, so we have tutoring day tomorrow, which means just show up, check in. If you have questions, you can ask those questions. If you don't, you can go. And you have a problem set due Friday by the end of the day. Problem set 2. And that's basically all we have coming up. Well, I was just looking at the calendar because had mentioned the test. The test is on the 18th, so we still have a ways to go for the test. So So we're going to start chapter 12, and then there is basically just 5 sections in chapter 12, and then those 2 things put together will be the first test. Test is open note, so just make sure you have some notes to use. Otherwise, I mean, it's mostly an honor system, but you're not really supposed to be using other stuff than your notes. So you can write down whatever things you think you might need for it, but yeah, make sure you're taking some notes so that you can use those. Yesterday we didn't finish a couple of the examples. I'm going to do those really quickly now. They're not super different than any of the stuff that we already did do, so I think it's should be too hard to use, but all right. So yesterday we were looking rectangular to spherical. We got almost all the way through, and then we had a couple examples there at the end. Again, when I see stuff like this, x squared plus y squared plus z squared, that makes me think spherical is a good choice, because x squared plus y squared plus z squared is rho squared. 4z would be 4 rho cosine phi. 0 is 0. I can divide both sides by rho, since every side could be, stop it. And then, so I have rho equals 4 cosine phi, which again, that's a simpler thing to deal with. Always be thinking like this will be an integral thing, and integrating a cosine is going to be easier than integrating something with x's, y's, and z's in it. This is just a sphere that's been shifted. This part looks like a sphere, the x squared plus y squared plus z squared, but then we have this little extra piece that wasn't kind of in the parent graph of any of the quadric surfaces that we looked at. That's just because it's been shifted. So think we could see what this looks like if we completed the square. So we did plus 4 minus 4. This is x squared plus y squared plus z minus 2 squared equals 4. So it's a sphere that's just been shifted up to 2 units. And if you shift it up and then kind of like multiply it all out, that's what's going to give you these extra z's or x's or y's or things like that, is after you've multiplied it out and kind of added things up and stuff. So, yeah, that's a sphere. Again, not the end of the world if you can't tell that it's a sphere, but if you can see stuff like that, that's good. Okay, coordinate-wise, we're going to convert rectangular to spherical here. Rho is the square root of x squared plus y squared plus z squared. So square root of 4 plus 16 times 2, 32. So square root of 40, or 2 root 10. Theta is the inverse tangent of 2 over 2, y over x. So that's pi over 4. And then phi is the inverse cosine of z over rho, which this is what we already found here, 2 root 10. So inverse cosine of 2 over root 5. Okay, and that's not a unit circle value. If you want to put it in a calculator and get an answer, great. If you want, you can just simplify it to the point like this, and you can just stop. It doesn't really matter to me either way. Unit circle values you should be able to do, but if it's not, then don't worry about it. Okay. So here we're going to convert from spherical to rectangular. So this is my rho, my theta, and my phi. X equals rho sine phi cosine theta. And so again, you don't have to evaluate the sine of pi over 9 if you want to. Oops, I didn't put the row in there, sorry. It's 12. The pi over 9 you don't have to do. Cosine of 3 pi over 4 is negative root 2 over 2. So this will be a negative 6 root 2, whatever sine of pi over 9 is. Again, I'm fine with you leaving that in there if you want to. Y equals rho sine phi sine theta. So only difference there is sine is positive. So I'll have a positive 6 root 2 sine pi over 9. And then z is rho cosine phi, which you can just leave because that's not a unit circle value. Okay, so that's it for yesterday's stuff. Converting back and forth. And again, we'll kind of focus in more on that when we get to integrals. For now, just trying to kind of get a little bit of an understanding of how that works. There. All right, we're moving to chapter 12, which will be when we first start seeing, some derivatives. So on Friday, we're basically going to have a quick derivative integral review, where you guys are kind of trying to review how to do some calculus stuff, because we're going to use that and then keep on adding to it. So we're just going to review thing. You guys can use the calculus memory sheet on Friday that I put in Google Classroom. You can use it on homeworks in the future as well and stuff. If you forget some formulas and stuff we learned last year, the goal would be that you just kind of refresh your memory on some of the stuff you may have forgotten, so that this year, as we add to it, you don't have a hard time doing what we've already done. Okay, so they were looking at what are called vector valued functions. End of chapter 11, we were talking about how normal functions graph as surfaces, and we basically need parametric equations to graph a curve. So like if I graph y equals x squared, in 3 dimensions, that's not going to graph as a parabola. That's going to graph as a surface that's shaped like a parabola. If I want the parabola itself, I have to use parametric equations. Okay, so like I would want x equal t, y equal t squared. That would graph a parabola. So we use parametric equations. We use what are called vector valued functions, because it kind of takes those parametric equations and puts them into one equation that we can then work with. So plane curves just means 2D. So we can get an ordered pair, f of t, g of t, which are the parametric equations, x equals f of t, y equals g of t. And we've seen parametric equations before. We used them at the end of last year. You've used them in pre-cal and stuff before. It's just getting a function that describes f and g separately. The benefit here is the actual curve may not be a function, right? We can get curves that do like go all over the place with parametrics, because the f is kind of independent of the g, so you can kind of get more interesting curves and things like that. So parametrics are good in 2D, even though we don't always need them. They're good because we can kind of express way more types of curves with parametrics than we can normal functions and stuff. When we say a space curve, that's 3D. And it's the same idea. Okay, so sort of like the very first couple lessons where I was like, it's the same thing, just add a z. With parametric equations, we'll just add another equation that describes what's happening with the z's. Okay, and again, this is really the only way we can do it in 3D, is to come up with equations for x, y, and z. Otherwise, again, if you just write a y equals 2x plus 3z or something, you're not going to get a curve, you're going to get a surface. All right, so vector valued functions are just taking each parametric equation and putting it into a vector. So like, we usually call it R, and these are vectors. Okay, notice this is bold. So we're just taking those parametric equations and putting them together in a vector. Again, kind of so we can have one single equation to take derivatives and things like that. We put them all together in one, and it's called a vector valued function. It's just the parametric equations. Okay, and then the way that the function works then is when I plug in a t, there's going to be a vector from the origin pointing to our location on a curve. Okay, we're not actually graphing the vectors, we're graphing where it's pointing to at any given time. So we'll have we may have a curve, and when I plug in t equals 1, it's going to tell me where I am on the curve. When I plug in t equals 2, it's going to give me a vector. It's going to point me at that location. So we don't actually graph the vectors. We're just saying this is pointing us to where we are in space or in a plane or whatever. That's what the vector value function is. So it does give you a vector, but it's the points, right? It's the end of the vector that we're going to actually graph. So yeah, they'll kind of look like this. So the gray parts, we don't graph that part. Okay, we'll have this curve. The gray parts are basically the vectors we get. So say we plug in t naught, it's going to point us to the point on the curve where we are at whatever t naught is, and t sub 1, t sub 2, and so on. Okay, in space, same exact idea. The biggest difference with these is with our vector valued functions, they have a direction, right? If I plug in 0 and I'm here, and 1 and I'm here, and 2 and I'm here, the curve is moving that way. So kind of like parametric equations, we have kind of a direction. So if I have a parabola, it's actually, I have an arrow that's either saying the parabola is going this way or it's going this way. Okay, so it's directed, just meaning there's a direction. It's going some particular direction. Okay, so they're useful for several things, and we'll use them for both of these things. You could let t be time, which is common. We've done that a lot in math, and I'm sure you have in physics and science type stuff. But it could be time, and it could do stuff like our position, velocity, acceleration, those types of problems, stuff that's changing over time. Or you can also use it to just trace a curve and model something. So we may want to model the shape of an atom, or the path of the electrons going around a nucleus or something like that. We can model that where we're not really concerned with the t corresponding to any particular time. We just want the shape. So sometimes we do that as well. And those are kind of the two main things we would use, is I can model a situation like when we were in school, and I don't know, we used to do a roller coaster project this quarter. I don't know that we'll really do it because I don't know how we would do it, but that one would be the second thing. We modeled the roller coaster. We made a roller coaster by modeling using vector valued functions and curves and things like that. Okay, so it's important to know that multiple vector valued functions can graph the same graph. Like these two things will both give me a circle. Sine ti plus cosine tj, that's a circle in the xy plane. So is sine t squared I plus cosine t squared j. It's the same physical form, right? It's a circle with radius 1. But they're traced in different ways. So like if you are wanting t to represent time, they're not moving in the same time, right? Like I graphed 0 to pi over 3, 0 to 2 pi over 3, 4 pi over 3, and 5 pi over 3. And so on that first one, you can tell it's moving around the circle. As I increase pi, I'm going to get more of the circle. On that second one, notice it's already closed the circle by 4 pi over 3. Like at 0 to 2 pi over 3, these are not the same. And at 4 pi over 3, these are not the same. Okay, so even if you can come up with a different set of parameters that make the same shape, that's great if all you're interested in the shape. But if you're interested in like modeling something over time, they aren't necessarily the same. Okay, so just know there are multiple ways to come up with a graph, a shape. But if you're interested in like time mattering, you don't want to just pick anything. There. Okay. Domain. A lot of times it's specified, so it'll say, like I did on that last one, 0 to pi over 3 or whatever. If it's not, the domain of a vector valued function is the intersection, meaning what the domains of each component have in common. Okay, so if I was coming up with like the domain of natural log of ti plus square root of 1 minus tj, I would think of the domain of the natural log of t is 0 to infinity. And then I would think of the domain of the square root of 1 minus t. And that's that 1 minus t has to be greater than or equal to 0. Which means t has to be less than or equal to 1. So I'm going to have negative infinity to 1. Oops, negative infinity to 1. And so we're looking for the domain of the vector valued function is the overlap of those two things. So if I can go from 0 to infinity on one and negative infinity, 0 to infinity on the first one, negative infinity to 1 on the second, my vector valued function is really only going to work from 0 to 1. If I try to graph this outside of that interval, I'm not going to get anything. Okay, so when we're looking at domain, we just want to find the domain of each piece. It's like here, domain of e to the t is negative infinity to infinity. Domain of that quadratic t squared plus 3t plus 2 is also negative infinity to infinity. So the domain of r of t is negative infinity, negative infinity to infinity. Okay, so if you're looking at domain, where does the thing work? You're looking at the domain of each piece, and we're getting the intersection, the overlap, the thing they have in common, the domain parts they have in common. Okay, so if we're sketching curves, you can always do a T-chart if you want. I would really say there's kind of two options. We could do a T-chart where we pick T's and we plug them in for the X's and Y's and get points and plot those points, right? So we could, looking that we have sines and cosines, we could pick something like 0. X is going to be 2 times the cosine of 0, which is 2. Y is going to be negative 3 times the sine of 0, which is 0. So we'd have a point over here. We could pick other easy values like pi over 2. 2 cosine of pi over 2 is 0. Negative 3 sine of pi over 2 is negative 3. So we're going to be down here. You can pick things like pi. That's going to give me a negative 2 and a 0. So I'm going to be over here. And then you could pick something like 3 pi over 2, which is going to give you 0 and 3, which is going to be up here. And our curve is starting here, going around here. And again, it's directed, meaning you should have like an arrow kind of showing which direction this thing's heading. It's going clockwise. This is an ellipse. If you weren't sure what was happening in between, you could graph more points, right? We're not sure if it's curving or something in between, but it's an ellipse. And I would get really used to seeing if your components are like sines and cosines, a lot of times that's a circle or an ellipse or something like that. Your other option is you can come up with the kind of rectangular form of a 2D curve, right? We could eliminate the t's altogether. With sines and cosines, the way I would do it is I would take x equal 2 cosine t, y equal negative 3 sine t. And instead of solving for t and plugging it into the other, which I would do maybe if it was a more algebraic thing, I would solve and isolate the cosine and the sine, because we have another way that we could get rid of those. So x over 2 is cosine t. Y over -3 is sine t. And the reason you get kind of this circular motion with sines and cosines is that we can say cosine squared t plus sine squared t is equal to x squared over 4 plus y squared over 9. And cosine squared t plus sine squared t is 1. So we can eliminate the t's if it's a mix of cosines and sines by using the Pythagorean identity. So 1 equals x squared over 4 plus y squared over 9. And notice we're now into the form we're used to seeing for an ellipse. Okay, I've got a radius of 2 in the x direction and 3 in the y direction. That's what these numbers stand for down here. So either one of those will work. I'm fine really with either. You do need to know how to do this, or at least start thinking about how you would do this, because that will encounter stuff like that in the future for sure. All right, so same idea here. With algebra, you kind of have hints of what's going to happen. We've got a t to the first and a square root of t. This is going to be a square root curve. Right, if x equals 1 minus t and y equals the square root of t, well then t equals 1 minus x, and I could sub that in here and I have y equals the square root of 1 minus x. So I can kind of see that in the parameters themselves. If x is a t to the first parameter and y is a square root of t to the first, then I'm going to get a square root curve. In this case, this is usually how we would think of what's happening here. So it's been shifted right 1, but it's opening to the left instead. Okay, or again, you could start plugging in t values. You have to realize you can't plug in t's that are less than 0. All right, sketching space curves, I wouldn't stress too much about because it's really hard to sketch a space curve. But again, you want to start trying to understand what's happening here. Notice in the xy direction, this is a circle. Okay, if we were to take x equal 4 cosine t and y equals 4 sine t, you want to recognize that's a circular motion in the xy direction. Okay, we're going in a circle because this is, x squared plus y squared equals 16 cosine squared t plus 16 sine squared t, which this is just x squared plus y squared equals 16 because cosine squared plus sine squared is 1. So I've got this circular motion going in the xy direction, but notice as I go around, as t increases and I move in a circle, the z's are increasing. So I'm not just going in a circle, I'm actually going in a circle and going upward. So I'm getting a spiral. Okay, this thing, as I move around, is going up. It's 0 to pi over 4, which means, I should have paid attention here. It'll go around once, it'll go around twice, so I should have not put so many of those. So it's going to go around 1 full time is 2 pi, and then 2 full times, and it'll stop here is 4 pi. So each full turn of the circle is going to be 2 pi to get around the circle. 4 pi will go around twice, and it's just increasing as it goes up. Okay, so we have things like, this is called a helix. Okay, and so that x squared plus y squared equals 16 that we get in the xy components, that's a cylinder. This is a helix, and it's a spiral that'll go along the outside of the cylinder. Okay, with radius 4. And so it goes along the outside and around. So you want to be able to start thinking about those parameters in terms of like, what is this going to do? How would I model this? A helix is a favorite one to show up a lot. Okay, and notice if we were to change the coefficients, that would just change the radius. If we were to start messing with this, it's going to change how fast it goes up. Right? If this was 2t, it's going to be stretched out farther. If this was 1/2 t, it's going to be compressed, the spring or the coil or whatever. Okay, but don't worry about your sketches looking great. It's hard to make your 3D sketches look great. Just do the best you can if you're ever asked to do it, and know that you'll never be really graded or counted off on a 3D sketch. So here, sketch the space curve. You should be able to tell this is a line, right? If I have x equal t, y equal 2t minus 5, and z equal 3t, that's a line. Okay, that's literally the equation of a line that we learned before. I've got a point at 0, -5, 0. Right? If I plug in t equals 0, for example, I've got a point there. I could make a t-chart and I could plug in like t equals 1 will give me the point 1, -3, 3. The problem is it starts to get hard to graph where that is. So like 1, -3, 3. Go up 1, 2, 3. You know, it'll be out in space like that. My dogs are going crazy right now. Hey, stop. And then, you know, you could keep on graphing points, and that'll give you 2, -1, 6. So you'd go 2 this way, 1 this way, 6 up or whatever. And you're going to get points that are going to be in a line. So it's more important to me that you kind of can see, oh, look, this is a line, that you can do the math with it. If you can sketch it, great. If you can't sketch it, it's not the biggest deal. But yeah, you could plot a bunch of points, and what you should see is they all lie on the line together. Okay. As far as representing a function as a vector valued function, this is just coming up with a parametric equations. If you have a function in terms of, you know, y equals x, y is a function of x, I would start by letting x equal t and find out what y is. If you have a function that's x equals f of y, I would let y equal t and just figure out what x would have to be. So 2D is pretty easy. If I have y equals x squared plus 1, I'm going to let x equal t, which means y equals t squared plus 1. And so I'd have a vector valued function ti plus t squared plus 1 j. Okay, and that would graph the same parabola as the y equals x squared plus 1. Notice that's not the only option, right? We could get the same shape by saying, you know, x equal t cubed plus 4t squared, and say, well, then that means y equals t cubed plus 4t squared plus 1. That's going to graph the same. It'll look the same. Obviously, the t's won't be in the same place. If I plug t equals 1 into 1 and t equals 1 into the other, I'm not going to get the same point, but the same points will exist along the curve. So if I graphed each one, I could do that. The simplest is usually if I have a function that I could at least solve to be one of these two. Generally, that's what I would do, is just let kind of the thing we can make the independent variable be t, and then the dependent variable be whatever the relationship is there. 3D is harder because I can't just pick one variable to be t, because often it's not easy to isolate or whatever. So here we're going to graph the curve, and this is how you come up with interesting curves, is you intersect different surfaces. So picture if we intersected an ellipsoid and a parabolic cylinder. So again, my graphing skills are not super awesome. Semi-ellipsoid just means half of an ellipsoid. So we're going to have kind of a bubble. And think if I took a parabolic cylinder and I sliced through this thing. Okay, picture what the intersection would look like. It's gonna go through this thing, and you'll have, I'm so bad at drawing, kind of this curve that goes around the cylinder, right? And that's the thing we're talking about. It'll kind of go up and around and over and down, where it slices through the part that's touching. So that's kind of what we're looking at graphing here. So like on the roller coaster project, when people are like, how do I come up with an equation? I would think of what shape did you want it to take, and you could kind of intersect these graphs. And so the way that we do that is I would take the simpler equation. So in this case, the y equals x squared. And I would go ahead and parameterize that. So y equals x squared is easy. We're going to let x equal t and y equal t squared. And then I'm going to plug that into the more complicated equation. So x is t, so this will be t squared over 12. Y is t squared, so this will be t to the 4th over 24. And then I have z squared over 4 equals 1. Now I can solve for z, right? I've basically found the points on the sphere that correspond to the points that are on the cylinder as well. And now I could literally solve for z. Z squared over 4 equals 1 minus t squared over 12 minus t to the 4th over 24. So z squared equals 4 minus t squared over 3 minus a t to the 4th over 6. So z equals plus or minus square root of that thing. Oops. T squared over 3 minus t to the 4th over 6. Okay, and then you just look in the problem. They said we want the top half, which means we're going to take the top half and just take the positive part. So those would be my three components. Okay, if I graph the curve, r equals ti plus t squared j plus that stuff, square root of 4 minus t squared over 3 minus t to the 4th over 6k. Okay, if I graph that in some graphing software, I'll get the curve moving along the outside of a sphere in the shape of the parabola. Okay, so that's kind of how we can generate more interesting curves rather than just kind of like making something up, is if we're trying to be strategic and you're like, I want a curve moving around a sphere, well, you can intersect different 3D objects and look at the way they intersect, and you can graph those functions as well. That's probably about the hardest that like coming up with one would be. Otherwise, continuity is the same as domain. If you're asked to discuss continuity of a vector valued function, you're just looking individually. This is continuous, right? X equals t is continuous at t equals 0. A is just a constant, that's continuous at t equals 0. There's a parabola, continuous at t equals 0. And remember, if you're not sure, you're basically looking for like things that make denominators 0 and stuff. We're looking at where is the limit as t approaches 0 of each of those parameters is the same as plugging 0 in, and same with y of t, and same with z of t. I don't really need you to prove it, prove it using the definition. But if you're not sure, remember that definition. If I'm looking at an individual part, if I found the limit as I approached the value, in this case like t of 0, is that the same as just plugging it in, or is it going to be something different? Okay, but basically we're looking, is there a vertical asymptote? Is there a hole? Is there something weird happening at any part? Then it's happening on the whole function. So continuity, again, I'm not looking for you to like prove anything crazy there. And that's it. Anybody have any questions on that? That'll kind of be the basics of a lot of stuff that we're using. If you ever need a curve in 3D, we're talking vector valued functions. So it'll show up quite a bit in this class if we're ever doing 3D stuff. That's our curves are made of that. But I guess that's it. So tomorrow we have a review day. Friday, we're going to do a actual, like a structured review on derivatives and integrals from last year. And then Monday we'll have another lesson. So we're done with lessons for now. If you guys don't have any questions, you guys are good to go. And you guys have a good morning, good day. And I'll see you guys tomorrow.
Thank you.
Thank you.
Thank you.
Bye, guys.
Bye, thanks.
Thank you.
Thank you.
Thank you.
You're welcome.
Maybe